these Venn diagrams to show that. Here's what, this is a Venn diagram. You know, your finance, your MIS or marketing, and there's no overlap there, so they're mutually exclusive events that occur. But is it possible that they would overlap? What would we do with that? We would have to subtract it, which I'll show you here in a second here. See what we're saying here? Probabilities that non-mutually exclusive events. This is a non-mutually exclusive event. Again, this is finance, this is marketing, but there's some overlap here. Well, these people are both finance and management. We have to subtract that out. Again, don't worry about it. You know, I'll show you, I'll give you the old red flag here that you know what's going on the test. So these are non-mutually exclusive events of A and B. They can both occur, but if they occur together, we have to subtract it from the probability of A. So the probability of A plus the probability of B minus the two of them both occurring, and we'll give you a nice example of this. And there's an example on the test that you shouldn't have any problems with either. So again, these are joint probabilities. So here again, the MF in the middle, that could be Massey-Ferguson or whatever you want it to be there, right? And here again, there are cumulative probabilities. And if you get SPSS, the SPSS will do all these things for you. It'll do chi-square. It'll do ANOVA. It'll do regression. You don't even need me, right? But, here you got A. There's a 10% chance. Now, B, there's a 20% chance. So 20 plus 10 gives me my 30. 30 plus 50 gives my... This is a cumulative as we go along, right? Again, baby statistics, you guys have had all this before. So what's the probability a student will get a grade of C or higher in my course? Right? 80%, right? Because you got the probability of A, which is 10%, plus the probability of B, which is 30%, plus the probability of C, which is, probability of B is 20%, the probability of C is 50%. Add those up and, right? So what's the chances that you're going to get? Probably 100% that it's going to be greater than, because you guys will bring out that rope and that knife and the gun and run me over in the parking lot if I gave you a C, right? So again, some events will affect each other and other ones don't affect each other. And we'll show you this again pretty shortly here with flipping a coin and picking balls out of a, out of a bucket. But we have marginal probabilities. We have conditional probabilities. The condition depends upon whether it's heads or tails, depends which bucket we go into. So it's a probability that an event will occur given that another event has already occurred. Flip the coin, tells me which bucket to go into. I go into that bucket. Now that bucket has different white, blue, red balls in it. Again, probability of A and B is equal to probability of A times the probability of B, and the probability of A, given that we know what the probability of B is equal to the probability of A. So here again, we're going to flip a coin. Probability of heads is 50%, right? Probability of tails is 50%. If we flip it again, what's the chances? Do they change? No, they're always 50-50, right? Remember that they said what's behind door number 1, door number 2, door number 3? Want to make a deal? Too young for that? Right? And he said, once you got past that first door there, do you change it or do you keep it? No, you keep it because thank you for the extra 33 1/3%, because, you got past that first one where you had a 1 in 3 chance of getting it right. And now, now there's only 2 left, right? So you want to trade it? No, don't trade it. Stick with what you had originally and take that extra 33% there. Go through the math and it should make sense. Here again, so what's the chances that I would get? I'd flip the coin, I get ahead. What's the chances? 50%, right? Flip it again, what's the chances? 50%. So what's the chance that if in 3 times I flip that coin, I'm going to get ahead? I flip it, I get ahead, flip it, I get ahead, flip it, I get ahead. What do I get? 0.125, right? Same as it is for tails, right? And the same as it is for 2 heads and 2 tails and a head. Tail, well, the sequence matters here too. A tail, a head, and a tail. Again, what's this going to add up to? Right? Should add up to 1, right? And it's deterministic. Why is it deterministic? So here's a good example why it's deterministic and why a priori we know ahead of time what's going to happen. Because can you guys come up with another combination other than it landed on its side? Is there another one besides 3 heads and 3 tails that would occur there? So that's, basically that's what you're telling you here. Probability of a head followed by a tail by a tail is the probability of a head times the probability of a tail times the probability of a tail. 0.5, 0.5, 0.5, multiply them together. How bored are you guys yet, right? Go home and watch the video tonight and see if you can keep up with my eye movements here, right? So, Bernoulli's process. You know Bernoulli? You guys, anybody watch Da Vinci's Demons lately? There's like some softcore porn in there. It's on Showtime or Stars or one of those, right? You got to throw that in. Almost all these are the same. It's just a different period in time, and they're having sex with each other. But Bernoulli's process, right, is when you fly in the air faster and slower over the top and the bottom of the wing. But also here, again, there's 2 possibilities that will occur here, right? Heads or tails. Probability of the outcomes remains constant over time. There's, like we said here, we flip those coins here. There's only so many possibilities. They're independent of each other. You flip that coin, it doesn't remember. That's what they tell you with a quarterback. He throws an interception. He has to have a short memory, right? Because it doesn't mean he's going to throw one the next time. Probably not a 50-50%. What are the chances? What's the completion rate for Roethlisberger? Is he 80%? Is he 60%, 7%? What's his rating? I don't know. But again, he's not going to, in 1 year, probably not going to vary too much. He might have a bad game. They're independent of each other. Just because you had a head the last time doesn't mean you're going to, chances are different that you're going to have a head or tail this time. And they're discrete, meaning that there are only so many only so many possibilities, and they're integer, meaning that they're a whole number, right? There's, it comes out to 1. So, does this look familiar at all? Have you ever seen this before? I got a nice picture of my coffee cup right there on that one. See, so you guys will see that after the end. This is what was on Moneyball, right? And so you think about this in terms of a pitcher, and how many pitches they throw and whether they're inside or outside a batter, whether they're better at the outside of the part of the plate, the inside part of the plate. This is what Jonah Hill used there in that software, and this is what the Oakland Athletics based their statistical probability on this binomial probability distribution. So again, we can easily get all mixed up. If you're not already mixed up, I'll go back and forth, and I soon will be. But notice that there's different, letters there, right? P is the probability of a success, right? And that's what we want to know. What is the probability of a success, right? And Q is 1 minus P because P plus Q has to equal 1, right? Now, again, if we're going to use a coin, what would be the numbers here, P and Q? What would P be and what would Q be? P would be 0.5, right? Q would be 0.5, right? Because it has to add up to 1. And number of trials, how many times are we going to do that? How many times did I come up to the plate and swing, and how many of those were outside, how many were inside, how many times were I successful and I got a hit, how many times didn't I? And R is the number of successes in N trials. So how many trials did we have? I threw the dice 9 times. How many times did an even come up? How many times did an odd one come up? Those are the type of questions we're asking here. So this is what we do. So determine the probability of getting exactly 2 tails in 3 tosses of the coin, right? So again, what's the 3? Here's the 3. We're throwing it 3 times. What does the 3 say, right? 3 is the N, right? What's N? Number of trials. Number of trials. Throwing it 3 times, right? 2, down here. What's the 2? 2 is the R. What's the R? Number of successes. We want to know how many of those, exactly 2 tails and 3 tosses of the coin. So that's why that's a 2. We want 2 out of 3, right? And we just follow the math. We go through it, and what's the probability come out to? 0.375. Again, do you follow that? Or easily for me to get messed up, easy for you to get messed up, but if you go back and forth and substitute these in, fairly easy, right? Like I said, silence comes over the crowd, right? Now, here's the thing. If, dead cold, I ask you to take the test and didn't give you another example of this, you might be in trouble. You're still going to have to go home and go over it. But when we're done with the lecture, give me a chance here. I'll give you another example, and we'll go over it exactly which one, how they fit in. Let me move on so I can cover the information. You know, I'm sorry, but you know, I can use to say that it's hot in here, or that I'm just stupid or whatever, you know, but we will regroup at the end, and I'll give you actual examples. And, you know, wink and nod, some of those are actually on the test, right? So, of course, you're going to pay a little bit more attention because, you know, I'll never see this sumbitch again, right? You know what I mean? But, hey, that one on the test, it's like my grandmother. Oh, hey, hell with that. I know that one's, that's B. Move on to the next one, the one he didn't give me, right? But that's all part of the game, right? You're with me, right? You're part of the team, right? I'm just the leader of the club here tonight, right? There it stopped. 20 minutes. Hey, nobody threw any raised